I guess it's my email address. Oh, how did they get it? I don't know. Hi. We're on the air. What were you doing? We're talking about some different elements and different concepts applicable to classifiers and regression machines. We talked very quickly about the idea. Let me get dressed here. I have a little monitor right in front of me. I can see myself. Do you ever try to do something in a monitor while you're watching yourself? You can't do it because you move this way, and so okay, I can't button myself. Okay. We were looking at the Curse of Dimensionality last time and realizing that, well, in some instances we might be able to perform an operation which reduces the number of features. There were two ways to do this. One was the feature selection, where we looked at this big list of features and were to choose a subset. And the other is feature reduction. Now, they sound very similar, but they are different. And we're still talking about feature selection. We mentioned the idea, for example, of finding the best features, and we decided that the best n features were not the n best features. You got to think about that statement for a while before you realize what it means. And that in order to choose the best team of features, in order to do your classification, if you wanted to choose a subset, you would have to do a combinatorial search, which really becomes very, very large. Now, there are enormous ways of doing combinatorial search, and we mentioned a suboptimal, which is to choose the best person for your team, and then choose the best person to work with that best person, choose the best person to work with these two, etc. But we decided that that was suboptimal also. So for this reason, we use different techniques, and one of them is dynamic programming. You can't see that, can you? Okay. Uh-oh. Big catastrophe. Well, let's look at the overhead, because what I want to do is I want to go down and make sure we know where we're on, what we're doing. Curse of Dimensionality, feature reduction versus feature selection. We talked about the difference between that. The main difference is that feature selection means, again, you choose the samples. Feature reduction is when you combine samples into a composite sample. Say you might have, as a very simple illustrative point, you might have the side and the length of rectangles. That's two pieces of data. Well, maybe you could just combine them and use the area, which is one number instead of the two numbers. You're still using all the information, but they're combined in some sort of fashion. There's different reasons that you use these. You use feature selection typically when there's an expense associated with getting numbers. If there's an expense associated with your data, then you might want to do feature selection, such as if you were doing quality control off an assembly line or something. Each of your tests is going to cost you money. However, if the data is coming in and it doesn't cost you any money, then you might want to consider feature reduction as opposed to selection. We wanted to talk quickly about the idea of dynamic programming and choosing features. Here's an example of the use of dynamic program in the case of Fisher distance. We said that last time that when we added a dimension or we added a feature to our set, that the Fisher distance would increase. Maybe you've thought about it since that time, but remember, with Fisher distance, the farther they are apart, the better we can discriminate among the two, because the Fisher distance is the distance of the means, if you recall, divided by the standard deviation. So let's talk about the dynamic program for optimality for a Fisher distance sort of thing. The idea is that one starts out with four possibles, and I'm going to do it with four features, and we want to choose maybe the best two or something like that. And this, for pedagogical purposes, typically, I've seen companies that have literally had thousands of different features from which they had to choose, and their features cost them money too, so they needed to pay some bucks to get the features. So let's take a look at this. Now, 1, 2, 3, 4, as we come down here, what we're going to do is we're going to delete one feature. I'm actually making a table of different sorts of combinations. So here we're going to delete feature number 4, here feature number 3, feature number 2, and feature number 1. So that here we have the features 1, 2, 3, here we have the features 1, 2, 4, and here we have the features 1, 3, 4, and here we have the features 2, 3, 4. Now, if we have 4, you notice up here we have chosen 1, so we have 4 choose 1 features up here, which is a total of 4 choose 0. We have 4 features, we have omitted 0, so there's only 1 combination. Down here we have 4 choose 1. 4 choose 1 is 4, which means we have a set of 4 features. How many different ways can we remove a single feature? It's 4 choose 1. We go down to the next step, and we can go 1, 2, 3. So here we have 2, 3. We have 1, 3. We have 1, 2. Here we have 1, 2. So that we have 2, 4, and we have 1, 4 here. And we come down this way, and we have 1, and we have 3, 4. Now you notice that the tree isn't totally symmetric because right here I omitted 1, but I don't want to omit 3 because if I omitted 3 I'd have 1, 4, but 1, 4 is already here. So it would be redundant, right? Again, if I took this result and I were to omit 3, I would get 1, 4, right, as a possibility. But 1, 4 already exists. So in going across the table, I only put on those branches which give me new and unique subversions of them. And then we can go on, actually. Notice this is 4 choose 2. What's 4 choose 2? Clearly it's 6, right? Because out of the 4, how many different ways can you take away 2? And then we have one more way of going down, which is 2, 2, and 3, which goes down to 3 and 2, and this one goes down to, if we take away 3, we get 1, and finally down here we're at 4 choose 3, which is 4, which means we've taken 3 of these animals away. Now, here's what we're going to do. I put up this graph to just show you from the start. We start with all the features, in this case 4 of them, and we begin to reduce these features one at a time. Yeah?
Should there be a line that goes to a 4 option also?
Oh, there should, shouldn't there? I forgot my 4, didn't I? 1, 2, 3, and I guess I got to go over here, take away 2 to get 4. Yeah, thank you. Right, because there was only 3 down here. I'll draw that on my notes so I don't screw up next time. Now, here's the point that we'd like to do in the feature selection for dynamic program for optimality. We would like to choose the best 2 features. The best 2 features, not the 2 best. The best 2 features, which means we want to choose here in some sort of fashion. We want to choose one of these. We want to choose feature 2, 3, 1, 3, 1, 2, 2, 4, 1, 4, 1, 3, 4. Now, in order to do this, we could do a exhaustive search. But again, if n, and in general we have an n choose k sort of thing here. K is equal to 0, k is equal to 1, k is equal to 2, k is equal to 3. In general, we have n choose k as we go down to the kth level. Where n, in our case, of course, is equal to 4. And this n choose k, especially when k is in the middle of n. K is n over 2, for example. Those numbers get humongous. They get very, very large. They get smaller at the ends. So we have this situation, and we have to typically do an exhaustive search here. Now, suppose that our goodness measure here was the Fisher distance. If it was the Fisher distance, we would have to compute the Fisher distance for all of these elements. But what is nice about dynamic programming is that it lets us stop things at higher places. Let me show you for an example. Suppose that in our Fisher program, the first thing we do, let's see, do I have 1, 3, 4? Yes. Okay, step number 1, for reasons we won't elaborate. Step number 1 comes down here in our dynamic program. So this is step number 1, and let's suppose that we find in step number 1 that we have a Fisher distance of 3. Okay? Now, what do we know? If we add features, we increase the Fisher distance. If we take away Fisher distance, we do what? We decrease it, right? I'm sorry, if we take away features, we decrease the Fisher distance. So we know that if we go down here, we're going to get a smaller Fisher distance because of the removal of these things. So here we have the first step. We get a Fisher distance of 1. Now let's go through the second step. And we will go through the second step down here to 3, 4. And so this is the second step. And in the second step, we get a Fisher distance of 2. And you notice that's consistent because we have reduced the dimensions. Therefore, we've reduced the features. So therefore, we have reduced the Fisher distance. Okay? So suppose now that, okay, so the bottom line here is 2. The bottom line here is 3. Suppose, just to illustrate now, that we were to come down here, and this was our step. I want to do this the same way that the notes are. No, let's come down here. And this is step 3, which gives us a Fisher distance of 4. And then we come down here, we give the step 4, which is a Fisher distance of 3. And here we have step 5, which is a Fisher distance of 2. Notice that we're consistent here. As we go down the tree, the Fisher distance gets smaller and smaller. Now, the dynamic programming comes here. Suppose that we go to this point and we find out that in step 6, we have a Fisher distance of 2. So we come down here, and 1, 2, 3 gives us a Fisher distance of 2. Notice we don't have to go down that tree anymore, do we? Why don't we have to go down that tree anymore? We don't have to go down that tree anymore since this value is achieved here. Maybe it would even be better if we made this a little bit smaller. Say this was 1.9. Okay? We know that going down this tree any further, we would generate numbers less than 1.9. We already have a result wherein the Fisher distance is 2. So we know we can get 2. Why do we want to search for things less than 1.9 when we've hit 2? So immediately at this point in the search, we can just cross that out and say we don't even need to go there. We don't even need to search through this branch anymore. And this is the concept of dynamic programming. As you go down to different layers, if you get a result down here, and this result, this final result, is worse at a higher level, then you don't have to search that tree anymore. So therefore, you have the ability to truncate your search before the end. Does that make sense? That's the essence of the searching for the best. Now, will this give you the optimally best solution? What do you think? Will it give you the same optimal solution as a global search will? Yeah. So we can go through feature selection of that sort. Let's talk about feature reduction now. Feature reduction is the combination of features into something which is more palatable. For example, if we were to have x2 and x1, this is directly from the notes that I made available to you. We're going to have these features. We're going to have these. Well, you notice a couple of things about them. First of all, we have a case here where we do not have linear separability. We want to separate the blue from the green, but we do not have linear separability here, do we? So therefore, we cannot use a Fisher distance sort of animal. We have to use something a little bit more complicated. There is a method, however, where we can combine these. Suppose, for example, we make a new value equal to x1 times x2. That is, we simply multiply those features together. We multiply those features together and we get a new result wherein, and you notice this is clearly cookbook as a pedagogical thing, that all of the green things multiply to 4, right? Correct? And all of the blue things multiply to 3. So all of a sudden, if we use this vector, if we use this feature instead of these features, not only do we get a reduction in the dimension, but we get a case where we can do a linear discrimination wherein we couldn't before. I have seen people actually in classification begin to look at features, and they made a big list of features where they were doing their feature reduction or selection. Then they would do other things. They would augment the list of features by putting the log of a feature on, by multiplying 2, by dividing 2, and putting those as kind of new features to see which one fit their classifier the best. So this is a possibility too, and this is feature reduction. This is a cookbook, but it does a cookbook sort of solution, but it does indeed illustrate the idea that we can combine the features and get better results. Probably the most common technique for feature reduction is principal component analysis. Okay, guys, LE or AL? LE.
Well, what are you trying to say?
The main
main
component.
That is AL.
No, LE is a principle. You're saying the main feature reduction.
Yeah.
That's the principle.
That's something primary, though.
Primary, that's AL.
What's that LE also?
No, that's the principle, like the principles of thermodynamics or something like that, which is not a maximum.
Do you guys agree yet? Huh?
It's convincing. I was an English major.
Oh, you were? Okay. Well, that settles it.
I hope I'm not wrong.
That would be embarrassing, wouldn't it? Okay. What we're going to do. Yeah, we are. We're going to Webster. You know what? I have this great book here. I bet you we spelled it right.
All about the English major.
All right.
All about the English major.
Okay. Elemental P. Principal component AL. Very good. Okay, principal components. That's the way I had it on my notes too, but I don't trust myself. This is also referred to as eigenvalue decomposition or Carhonen-Loew analysis, and it is relatively standard. The concept here is as follows. One computes the center of mass. One has a number of points. And here's the basic idea between Carhonen-Loew analysis. Here's what we're trying to test. We have data in a high-dimensional space, and we can reduce the dimension of that data if that data lies on a plane or a line, a linear subspace. So therefore, if all of this data lies on a line, or let's do it 3 dimensions, x1 and x2, and even over here x sub 3. But what we find out when we get done is that there is this line here, and roughly all of the data is along the line. Then instead of using x1, x2, and x3, we can go along this line, call it z, and just use the value of z corresponding to whatever that is. Similarly, maybe a line isn't enough. Maybe in this high dimension, things lie on a plane. Okay? Maybe all of this data lies on a plane. And by the way, all of these go through the origin, as we'll see. So maybe all of the data lies not exactly on a plane, but very, very close to a plane. So therefore, if it lies on a plane, instead of using 3 numbers, we can use 2 numbers, say z1 and z2, corresponding to these new coordinates of the plane. Make sense? So therefore, we can take all of this three-dimensional data, we can reduce it to a one-dimensional data here. Down here, we can take the three-dimensional data, reduce it to smaller dimensions. The basic idea behind this is the same as that which we did in the Mahalanobis distance. The concept is the same. The application is very, very different. Remember that we said that with a Mahalanobis distance, we could take a we could take a bunch of data and we could fit an ellipse around that data, an ellipsoid. What happens if the data basically lies on a plane? If the data basically lies on that plane, then that ellipse is really flat in one of the dimensions. So what we're going to do is we're going to look at that ellipsoid and see if that ellipsoid is flat in one or more dimensions. If it is flat in one or more dimensions, that means that we can remove that dimension essentially in doing so. And we do this as follows. We first of all compute the mean and the covariance matrix. Now this covariance matrix is such that it has eigenvalues and eigenvectors, which I hope you've seen before. That is, there does exist a set of vectors, let's call it lambda sub n, so that when we multiply this by the covariance matrix, we get back something which is proportional to the original vector. You've seen eigenvalues before. Well, the interesting aspect of these eigenvalues is they tell us the dimensions of the ellipse on which things are fit. And if these lambda n's are big, that means that psi sub n is important. Because this tells us how much this eigenvector and all of these eigenvectors, should I write that down? I'm not sure how familiar you are with this idea. Hopefully it should be something which you've seen before. This is the eigenvector, and these is referred to as the eigenvalues. There's a very simple one-line command in MATLAB which you can apply and get the eigenvalues and eigenvectors. What is that? Is it just EIG? Eigen, E-I-G-E-N. And so you apply it to the matrix, and boop, all of a sudden you get all of these eigenvalues and eigenvectors. Now typically what will happen again is the following. If the lambda, this tells us how much this eigenvector is amplified. Lambda sub n is the amplification of the vector. For example, if lambda sub n is 0, then it's amplified by 0.00, well, it's amplified by 0, so nothing comes out, right? If it's a really big number, it means it's amplified a lot. Typical eigenspectra, and the lambda n's, by the way, are typically organized so that lambda n plus 1 is less than or equal to lambda sub n. So they're organized in decreasing magnitude. In certain cases, if you look at the lambda sub n's versus the n's, you will find out that it looks something like this. And it will go up to n minus 1 all the way from 0. So the n's go from 0 to n minus 1, whatever dimension the matrix is. And you'll notice that lambda, that the matrix itself is n by n. So we have these. Well, what this is saying is that the ellipse, which this data is fitting, is very, very important in these dimensions. And what the lambda sub n's do is they describe a new coordinate system for you, don't they? They describe a new coordinate system. They are orthogonal to each other. So originally you might have x1 here, you might have x2 here, and you might have x3 here. Well, these new eigenvectors are going to be different unit vectors. Like you might have psi sub 1 here, psi sub 2 here, and psi sub 3 here. And they are mutually orthogonal to each other, just like the x1, x2, and x3. And these psi's, these eigenvectors, tell you the orientation of that ellipse. In fact, this biggest, lambda 0, is in the direction of the biggest dimension of the ellipsoid, etc. So if you have, so in a way we can think of this as the thickness of the ellipsoid. So down here when we have eigenvalues which are very, very close to 0, it means that in that direction that ellipsoid is essentially flat. Thus, in general, we make an engineering judgment that says, well, what can I ignore? Because usually it isn't a clear-cut unit step. They just go down. And the more you choose, well, the better the representation is going to be, but the more features you're going to have. So one makes a choice where you make the cutoff, and let's say that we did, say n was equal to 1,000, and we were able to, with our eigenvalue analysis, say that the everything above a certain point, say 700, everything above the point was 700 was essentially 0. Then what we could do is we could use these new coordinate systems in order to generate new data and take our 1,000 cardinality of dimension and reduce it to 700. Okay? And the way we do it, is we simply place the original data into the eigen system of coordinates and use those coordinates, but we ignore the top 300 because essentially in the top 300 you're on a plane and there is no variation in that direction. Yeah.
So if we had a sphere in multidimensional space, it would just be a straight line across?
Yes, it would if we had a sphere. In other words, if your data was spherical, and think about this, it makes sense. If your data is spherical, all of the features are kind of equally important in a way, right? If it's on a plane, then the data is correlated in a statistical sense, right? Correlation is a measure of linearity, if you will. So this has a very nice property of being able to reduce the features because we identify that the data exists on a plane. It also means that some of the data is redundant to other data, doesn't it? If it exists on a plane. So we have removed the redundancy in the data. We might find out for basketball players that the salary is correlated with the height. It probably is. Maybe they're redundant features. Certainly one has to do with something. One has to do with the other. So we can do that. So anyway, this is a way of doing this. Now, there are some limitations to this. What is one of the limitations? One of the limitations is it's only applicable to when the data lie on a linear manifold. If you were, for example, to apply this, say you had some data, x, y, z, w, x, y, z, and this data was actually equal to w squared, w cubed, and w to the fourth. Clearly, this data has something to do with itself, right? However, this data, this curve is not on a plane, and singular value decomposition, which is what we're doing here, would not work in this case. So it's only applicable when the data are correlated in a linear sense, that all of the data exists upon a plane. If it exists on some other hidden manifold, then this is not going to apply. You might think that, gosh, there should be ways to do that. Okay? So that's a primary limitation of this. But it does turn out to be very useful because there is lots of linear redundancy in data, and this allows us to get rid of it and reduce the number of features. Now you'll notice this, unlike the feature selection, uses all of the data. When I find my coordinate in lambda 3 here, I need my x1, x2, and x3 component. I'm combining them in some sort of way. So I need all of my features, but I'm combining all of those 1,000 features into 700 other features, but I need all 1,000 of my original features. So therefore, I have not reduced the number of features chosen. Rather, I have used all of the features that I have, but I've combined them into a more efficient way, a more efficient representation for classification by reducing the degrees of freedom required to perform the operation of classification. I'd probably not. Okay. Does anybody understand what I'm saying? No one. Okay. The idea is as follows. We have, say, 1,000 data points, or 1,000 features, let's say. Feature selection would choose the, say, the 300 best. Okay? Feature reduction says combine them into 300 new features. But we need all of the 1,000 features in order to get this. Remember the example that I gave you where we simply had, I just erased it, where we multiplied the two features together to get another feature? We ended up with one feature, but we needed both the features to get that one feature. So that's the idea of feature reduction. We still needed all the original features in order to get the new composite feature. Whereas feature selection, we just choose a subset of the features. So that's the difference.
What we did with the singular value decomposition was selection.
No, it's reduction. It is reduction because, say I have a value x1, x2, and x3, and I have a data point here in x1, x2, and x3. Okay? Now, with feature reduction, or with singular value decomposition, what I've done is I've defined a new plane here, if you will. And I've said that all of my data is basically on this plane. I should include the point here. I've said that all of my data is basically on this plane by the singular value decomposition. Now, this new plane has coordinates of psi1 and psi2, where these are the principal components. I've ignored psi3 because that's the one orthogonal to this, and there's really not much variation of the data. So what I need to do here is I need to, in this new coordinate system, I need to determine the psi1 coordinate and then the psi2 coordinate, the expansion coefficients, if you will, kind of the alpha 1 and the alpha 2. So I need to determine where the weights are on this new axis, and in order to do that, I need all three of the original coordinates in order to do that. So I'm taking all of the three data and I'm crunching it into two, just like I did when I multiplied the two functions, except this is done, of course, with a matrix vector sort of multiplication. Does that answer your question?
Yeah, but if for some, I missed the first step. So if for some weird reason we already had our system in eigenvalue form, then it's really a selection problem, because we're just cutting off the unneeded dimensions.
If they're already in eigenvalue form, but that assumes, for example, that you have data which is directly related to itself. For the basketball player, you might have the basketball player's height and then the length of their leg. One is, I guess, 3 times the other one, say roughly. So they're already related to each other, so you can cut one off immediately. But not, that's a bad choice of words. But yeah, okay. Good. Okay. Let's see what else good stuff we have here for us. with the Fisher discriminant. Okay, so I guess we have touched all of these things which are pre-neural network classifier sort of things. We've touched on the curse of dimensionality, feature reduction versus feature selection, the difference between them. Feature selection, feature reduction. We've talked about the idea of dynamic programming as a nice method to be able to choose. And this isn't always a good method. You have to make sure that when you add or reduce something, that whatever metric you're using is decreasing or increasing in order to reduce your overall search. That is the case with the Fisher distance. And then we talked about principal components, which comes from the Carhonen-Loew expansion, which basically looks at an elliptical fit of the data and sees if that ellipse is flat enough in one or more dimensions, wherein those dimensions can be excluded in the actual classification. In other words, those dimensions are no longer important. Any questions on that at all? We had some homework where we had the, where is my little thing to make it big? Oh, there it is. Okay. We had some homework where we did the fuzzy regression machine fit to e to the 10th, and what was the lowest error we got? What was yours? 13. But you used Sagino. Okay. Some people did go to the fuzzy logic toolbox in MATLAB. That's okay. Anybody just try it with the min-max or the fuzzy product? Would you?
Scratch. I don't know. I used root mean squared instead of mean squared error, so my number was a bit different from other people's numbers. So
use mean squares.
I used root mean squared. So I think about.
Does that mean the square root?
Yeah. So about 90,000.
So we have to square that.
Yeah, 90,000 is what I got if you square it.
Oh, if you square it, 90,000, and you got 13,000. That's Sagino. Okay. Anybody beat 90,000?
60,000.
Whoa. Sorry. Oh, okay. It'll be fun to look at the results, and we might post some of the better ones just so you can see what happens. Again, this is the purpose of the exercise was not one where I wanted you to optimize with the man in the loop, but rather I wanted you to fiddle around with these things and hopefully have the concept of the fuzzy regression machine and its dynamics become more familiar to you. So you can see that we're essentially doing a curve fitting in sort. And that indeed is what we do. And I think you can see also that in such cases where we use a min-max or a Sagino or some product sort of logic, that once we come up with the result, that we can always tweak with the parameters in order to manipulate the system to become more and more accurate, to do more and more what we want it to do. That's one of the interesting reasons why fuzzy logic is so remarkably robust, is because we can apply any of these, and then once we have the final system, we can play around with the membership functions and such and tune it in order to give us a very good representation. The initial system, however, is just set up using basic concepts of taking linguistics and directly applying it to a system, which is kind of neat. Okay, let's talk about neural networks then. We're actually going to start in with the text, and we will talk about some of the different neural networks. How come I got? Okay, hold on. I wanted to start at the beginning. Okay, neural smithing. Okay, the introduction. There is always the obligatory statement in the beginning that neural networks are computers that try to work the way the brain does. However, as engineers typically do, we have taken the biological entity and we have manipulated it quite a bit that it deviates significantly from its biological counterpart. We didn't invent, for example, airplanes that flap their wings, right? Even though in all biological cases they flap their wings. So we did some different concepts. Here is from the book. If we could do one on this, thank you. This is from page 2, and it's a representation of a biological neuron to a actual artificial neuron, or at least the way artificial neurons are typically talked about. we have a so-called cell body, and this cell body takes on a state, a number, and this number is associated through the axon to a number of other different neurons. And the way this state is determined is one or two ways. This can be a cell which is connected up to a sensor, such as an eyeball, so all of these inputs are photon counts or something, I don't know. Or it can actually be an intermediate where the stimuli that actually generate and stimulate the cell are actually other neurons which have states which are stimulating the cell. And so this is a rough engineering equivalent to that. We have the following. We have a neuron, and this is a single neuron model, and it's the most commonly used single neuron model. And the basic concept is that the neuron collects data from other neurons or sensors. It weights them, and the weights is determined by the synaptic connection in the cell. That's the degree to which other cells can communicate to the parent cell. And so these weights have a biological counterpart called the synapse, and sometimes are even referred to as synaptic weights. So we have states of other neurons or sensors which are fed over some sort of synaptic weight, and then they are summed up. So the weighted sum is summed up, and then it is run through a nonlinearity. Typically, this nonlinearity is referred to as a squashing function. You'll notice that the way that it's depicted here, it's a function which has an S-shaped curve. An S-shaped curve is also called a sigmoid. Sigmoid meaning S-shaped curve. And the reason it's called a squashing function is because it takes a very large dynamic range and it squashes it into a very small dynamic range. Anyway, we'll talk about that in a little bit. But notice the interesting aspect here is that this nonlinearity exists and the neuron is a nonlinear entity. Something happens nonlinearly to it. So the output of this is referred to as the state of the neuron, and this state of the neuron can be broadcast either as an output or as an input to other neurons, which might be to the right of it. So this is much like a little building block, a little rubber stamp that we can stamp out, and we can connect a number of neurons. Let's take a closer look at the manner in which these are connected, number one, and number two, what that nonlinearity looks like. The most commonly used nonlinearity is called the sigmoid, and it's simply equal to 1 over 1 plus e to the minus x. You know, it's a strictly increasing function that goes from 0 to 1. You can see again why it's called a squashing function. And just about any function that goes monotonically from 0 to 1 can be used as a squashing function, depending on the manner that the training of the neural network, the manner that the training of the neural network is done. This is commonly used because it has very nice derivative properties, and that's about the only reason. It has some very nice derivative properties. Its derivative is equal to the function times 1 minus the function. So it has a very nice derivative property. But we could also use a hyperbolic tangent or a arctangent. That would work. Or an error function, right? That would work. But these are higher transcendental functions and they're more difficult to deal with. So this one is one which is used quite commonly. Again, it squashes because it takes a very large dynamic range and places it in a very small dynamic range. Now, these neurons are connected typically in a number of fashions. Here is a commonly way to connect these neurons. And this is referred to as a layered perceptron or a layered neural network. We have some inputs. These inputs are usually from sensors. If we're trying to perform a classification, these would be the values of the classification. So if we were doing jockeys versus basketball players, we would have x1 corresponding to the weight and x2 corresponding to the height. Now, these are actually not neurons on the input. They are sensors. Notice a neuron has to receive data, crunch it, and spit it out. And there's no crunching, or there's just spitting out, right? So these sensors actually broadcast themselves to the next layer, and this next layer receives all of these and then performs the summation, as we saw before, runs it through a sigmoid nonlinearity, and then whatever the output of that nonlinearity is the state of that neuron. This neuron then broadcasts to these output neurons, and these are neurons because they collect the values from here, run them through a summation, run them through the nonlinearity, and in this case they're output, because whatever the state of the neuron is going to be the output of the neural network. This could potentially be a classification, such as basketball player would be a 1 and a jockey would be a 0, or it could be actually a regression machine. It could be it could give us a continuous number. One of the things that we talked about, I think on the second day, was load forecasting in a neural network. So we might have, if we were forecasting the power load, we might have the current temperature, the forecasted temperature, the load which was used today, a number of different features, and then the output neuron would not be a classification in the sense of a Boolean decision, but rather it would be a graded response corresponding to the actual amount of load that we would expect on the previous day. So this is referred to as a feed-forward network. It's a feed-forward network because notice all of the arrows point up, don't they? There's no feedback mechanism. We could, for example, take this output layer and have a feedback into the hidden layer and actually have a feedback loop within the neural network itself. These are referred to as recurrent neural networks. Feed-forward and recurrent neural networks are a lot like FIR and IIR filters. And one of the reasons that we like feed-forward neural networks, for the same reason we like FIR filters, we don't have to worry about stability issues, right? All FIR filters are stable, and so we can be assured that all feed-forward networks are also stable. If you have feedback, you can get into some very tricky situations, especially when you have feedback with nonlinearities. That's the classic model of chaos, for example, and if one isn't careful, one can break into a chaotic sort of situation in neural networks also. So this is referred to again as a multi-layered perceptron. It is a specific type of neural network. Now, the relationship comes in the sense that we would like to establish an output for a given input. The manner that this happens, or the thing that controls this mapping, is the weights, the synaptic weights. Choosing of different synaptic weights are going to give us a different input-output relationship. You can think of this as a system, where this is the input and that's the output, and all of this other stuff here is the system. What we would like to do for a given database is we would like to train the interconnects, or the weights among the neurons, in such a fashion that the input-output relationship in some way mimics the database which is used to perform the training. So the real networks have synapses and cell bodies. Artificial neurons emulate the architecture. We've looked at the schematic, the equation for the neuron. Here is the equation for the neuron. Let me just write it on the board instead of showing you in the book. The equation for a neuron, taking the schematic that we showed you and reducing it to an equation, y is equal to f times the summation of k of w sub k times x sub k. That's a neuron, as far as an artificial neuron, in the sense that we have our input values, x sub 1, x sub 2, all the way down to x sub k. We collect them, and what do? We weight them, w sub 1, w sub 2, w sub k. Then we perform a summation operation on them. So the output here is equal to the summation result, right? Then we run it through f, which is the nonlinearity, typically the squashing function. And the output is y, which is the state of the neuron, which in turn is broadcast to different results. Notice we can also write this as a function of w times x, where this is simply an inner product. This is the summation for that inner product written out. So that's more of a shorthand notation for the same result. So that's what the neuron looks like. If we look at the overhead, we see how far we are from neural networks, biological neural networks. The brain has from the order of 10 to 10 to 10 to the 15th neurons in it. We're very far from that. And plus, the neural network that we have talked about is homogeneous. Each neuron is about the same as every other neuron, and certainly that doesn't allow for specified sort of reactions. As I mentioned before, the input perceptron inputs are not neurons, they are sensors, because they don't crunch data. The only thing that they're responsible for is taking the inputs, the sensor inputs, the feature inputs, if you will, and broadcasting them to the next neurons. There are two types of neurons in the layered perceptron. There are output neurons, which is where you take a reading, and there are hidden neurons. These are neurons which are not associated with an output. So for example here, these are the output neurons, and these are the hidden neurons. Okay? So there's two types. There's the output and the hidden neurons. Another thing is that the architecture need not be layered. There's a very nice picture later on in the book. Let's see, page 32, okay, verses 51. Here is another example of a feed-forward neural network that is not in a layered, not in a layered architecture. And the layers do not need to be specific layers. In order for a feed-forward network to exist, we should be able to do the following. We should be able to number things. We'll talk about the bias node in a minute. We haven't had a chance to talk about that. But we number the inputs 1 through 6, and then we number all of the other neurons. And when a neuron is connected to another neuron, it has to be connected to a neuron of a higher number. And all of the neurons feeding this neuron have to be of a lower number. So 8, for example, is fed by 7 and 1. Well, 7 and 1 in both cases are smaller than 8. In a similar fashion up here we have 14. 14 is feeding 15 and 16, but it has inputs from 12, 13, 10, and 11, and 3, okay? And all of those are numbers which are less. And as long as we maintain this ordering, we still have a feed-forward network. As always, the interconnects here have weights associated with them, and these weights are what ultimately determines the input-output relationship. So we put this up as kind of a far-out example of the observation that the layered perceptron need not actually be layered. It can be in a kind of sporadic sort of manner, and we are not confronted with feedback loops as long as we maintain the ordering which we show here.
So with the hidden layer, does that mean that the states of those neurons are hidden to you when you're trying to train the network?
It turns out that yes, the hidden layers, and I'll repeat because of the microphone, that the hidden layers have states which are not known to you during the training of the neural network. That's right. Because what you're interested in is interested in the input-output relationship only. And it turns out, as we will see, that these hidden neurons are required to give a neural network a incredible flexibility in terms of the manner which we can perform differentiation. We saw, for example, that the Fisher distance could only perform well on data which was linearly separable, right? The layered perceptron can be used for classifier problems where the two different classes are not linearly separable. They can be separable in some sort of very, very strange fashion. So it has a greater degree of flexibility, and it turns out, as we will see, it's these hidden neurons that give it this degree of flexibility. And we will see that if we did not have these hidden neurons, that we would be restricted to linear problems that the Fisher distance addressed. So yes, they are necessary. And you can see here, even in this more complicated schematic, that the identity of hidden versus output neurons are still very clear. we see something interesting here. This output neuron, which is Y1, also feeds another output neuron. Oh, that's okay. As long as there's no feedback loops, it is still a feed-forward neural network. This particular representation is very useful for training and error-back propagation. In fact, is on page 51 and is used to illustrate error-back propagation training. Okay. So again, the MLP need not actually be layered. And again, we emphasize for a given architecture, the input-output relationship of the neural network is a function of the synapse or the interconnect weights. That is what determines the input-output relationship. So, given a data set that you would like to emulate the input-output relationship with, for example, the basketball and the jockeys, we would want to choose the synapses, which allowed a good classification, a good representation between them. Okay, let's talk about supervised learning and the difference between supervised and unsupervised learning. Supervised learning occurs when your data is tagged with a classification. You recall the iris data? Notice the iris data. All of you look at the iris data? Did you get good ROC curves, by the way, using the Fisher discriminant? You did? Was it 100%? Really? Which ones did you use?
1 and 2.
1 and 2?
2 and 3 weren't linearly separable completely, but 1 and 2 and 1 and 3 were.
Oh, okay. That's interesting. Okay. So very uninteresting ROC curves, right? Yeah. Just kind of a little unit step. That's okay. I forgot what I was talking about now. Oh, supervised versus unsupervised. If you're given those tags as iris type 1, 2, and 3, then you would use supervised learning because you have a supervisor saying, you have this data is for iris number 1. This data is for iris number 2. This data is for iris number 3. So you have a supervisor, a teacher, which is teaching you and allows you to know what the data corresponds to. There might be another type of data, which is unsupervised learning, where you do not have available this tag. Suppose, for example, I were to get in these jockey players versus basketball players, and I have the classical weight versus height here, and I don't know if they're jockey players. So I get all these guys in there and I measure their height and their weight, and they're not tagged as a basketball player or a jockey player. What I might do is stand back and say, well, you know, it's kind of like all these kind of look the same, and all of these look the same. Okay? In other words, the groups naturally form into what's referred to as clusters. So we perform clustering on the result, and then the cluster is used for the classification. But again, for unsupervised learning, we do not have the luxury of a tag for the data as far as its proper classification. We have to look at the data and kind of figure out, well, you know, things kind of separate here. This is, as you might suspect, an art. It does not have a unique answer, and is very, very data dependent on what sort of clustering algorithm that you perform the operation on. So that's the difference between supervised and unsupervised learning. Unsupervised learning is almost always associated with clustering. That at the end you have to look at your data and you have to cluster it in some sort of fashion. And then you have to ask questions about, what about the granularity of the clusters? Here I chose 2. What if instead I chose 8 different clusters? And I get tall basketball players and short basketball players and things like that. So that is the difference, again, between supervised and unsupervised learning. There is reinforcement learning, which is very similar to the result that you have with a Rosenblatt perceptron, where you don't tell the classifier how good or bad they're doing. You just say thumbs up or thumbs down. There's no error which is measured. It's just whether you're good or you're bad. It's kind of like teaching your dog to bring you the paper, and if it brings you the paper, You give it a piece of meat. If it does anything else, you whack it over the head. Okay. If it brings you the phone book, well, the phone book's not the paper, so you whack it over the head. If it brings you yesterday's paper, well, it isn't today's paper, so you whack it over the head. Even though yesterday's paper is getting closer to the idea, right? So reinforcement learning is just a thumbs up or thumbs down sort of update of the result. Supervised learning, on the other hand, usually takes into account the relative magnitude of the error. If the dog brought you yesterday's paper, you would just slap him really lightly, right? Whereas if he brought you a rock from outside, you'd whack him one. You get the idea? So that's reinforcement, which is kind of discrete, thumbs up, thumbs down. There's supervised learning, which allows relative error. And then there's unsupervised learning, which is the clustering. Now, once we perform an operation and we perform a choice of these weights in these neural networks, we have to decide for ourselves what is good. And we have to assign that what is good a mathematical statement, which is usually referred to as an objective function or an error function, if you will. And an error function is something that you want to minimize. And we have to decide what it is that we want to minimize. There are different ways to do this, and they're here in the text. One of them is the sum of squares error, which is probably the most common way of doing it. It's I. This is the sum of squares error. Now, the sum of squares error does the following. It takes an input into a neural network, a layered perceptron. And typically, the neural network actually has more than one output. It can have one output, but maybe it has a number of outputs. So here we have all of the interconnects. I'm not going to draw them because there would be a lot of them here. So we get the inputs here, and then we get the outputs. And the outputs are what we're going to call 1, or Y, say 1, Y2, Y3, and Y4. We are assuming that we have, I forget if it's P. Okay, P is the patterns in the set. Over here, to train this neural network, we have a list of training data. We have I sub 1 should give a result of target 1. In other words, if we put in these values of I1, we should get out T1, T2, T3, and T4, which is the T vector. But we have P of these, so we go down to I sub I P, and this goes T1P, T1P, all the way down to target IP. So this is our training data. Now our training data is fixed. Our training data is not a variable. It's like the iris data. It exists there, and it is going to determine the input-output mapping. And initially, when we put in an input and we get out a Y, the Y is what you get. Get. And the T, which is the target, is what you want. For a classifier, these target values are going to be 1s and 0s, typically, for a classifier. For For a regression machine, there'll be more of a floating point number. So you have outwards what you get, and you have what you want. The difference between what you get and what you want is going to be the error. So we actually take the difference between these and we square that error, and we add it up, but we add it up not only for the first input, but for all of the inputs. So we add it up for all of the data sets. So we put in I, we get one of these terms, one of these sums. We put another one, we get another one of these sums, and we sum up this error over the entire training data set. Get the idea? And this is what we want to minimize. Now you notice something which is implicit here is that this y, which is what you get, is a function of all of the weights in here. Let's just take all of those weights and just put them in a big vector called W. So what we would like to do is we would like to determine these weights such that, given this data set, we minimize the sum of the squares errors. Okay? If we do that, then this will emulate the database pretty well. It isn't the whole story, but it's the first chapter of the story. It's the first portion of the story. So, again, the entire idea is to look at this sum of square errors, which is a function of the weights of the neural network, and to perform an optimization on it such that this is minimized. When this is minimized, then the neural network, if this went to 0, we know that if we put in this, we would get out this exactly. If we put in this, we would get out this exactly. If we would put in this, we would get out this exactly, etc., if it were 0. Typically, it doesn't go to 0, and we'll see later reasons why we don't want it to go to 0. Because if we get it to go to 0, it turns out what we're doing is not learning, it's memorizing. We're not interested in memorizing, we're interested in learning, and we'll find out the difference there. But you get the idea as far as training a neural network, what the idea is for supervised learning. And in fact, this is always the case for supervised learning, for adaptive supervised learning. We have an input, we have an output, which is y, and we have a target vector, and we have in here a bunch of things we can wiggle. And I don't care what it is in there. You can put anything you want to in here, but the parameters of this system, that is things we can tune, correspond to these W vector. I like to think of them as little knobs. And each little knob, you have 1,000 knobs you can turn up and down in order to get a different relationship. And what you need to do is you need to set each one of these knobs corresponding to a different value of W so that this output is close to your target for a given database. And finding an intelligent way of twiddling those knobs in order to affect a good input-output relationship is training the regression machine. Now, this certainly is a generalization of this, right? In other words, the layer perceptron is a special case of this, right? But you could do this with anything. I could take just about any function that you can have. I could take any system that you can have, put a bunch of variables in it, a bunch of different knobs, and I could twiddle those knobs to get the best representation I have. And different systems are going to give me different errors here, different minimization of errors. So this is the concept of unsupervised learning, or supervised learning, I should say. I'm sorry. Any questions at all?
How do you take the error and affect your weights?
That's what we'll talk about next time. There are people that spend their entire careers in optimization, in operations research, that actually look at these sorts of functions in higher dimensions and find the arguments which minimize it. And we'll look at some of those different techniques and the ones used most popularly in training the neural network. So that's the next step. Okay, thank you. Check the web. I will have homework tonight.